All right. Okay. Welcome back, everyone. So let me remind you what was the definition again of competitiveness. So now we're gonna talk only about competitive ratio, which is a little bit simpler than online Lipschitz. So again, we say that an algorithm selector is alpha competitive if there is this some constant, which could depend on the metric space, but which doesn't depend on the sequence of requests, such that for any sequence of requests, the total movement of the selector on this sequence of requests is comparable up to this additive constant beta. It's comparable to the best you could have done in hindsight had you known in advance all the sequence of requests. Okay, so beta plus alpha times this, and then we say that the algorithm is alpha competitive. So this morning we saw a first theorem, which was that so on uniform space, we saw that marking or randomized marking is n competitive and O of log n for randomized. O of log n for randomized.
So Sebastian,
yes?
maybe one question. I don't know. Maybe
Yeah, please.
Now, before you when you were talking about this online Lipschitz version,
yeah,
the maximum or zero.
Yes.
We can kind of understand that with the beta is as long as the family is bounded, it's the same, right?
Yes.
Okay.
Yes. So this is exactly what I have in mind. So here I'm assuming that. So yeah, this is a good comment. So the two, because of the beta, one implies the other when X is bounded. And indeed, for instance, for the case of convex set, it is unbounded. So then, for the case of convex set, one thing that people usually talk about is to fix the starting point in this language. But in fact, for convex set, you can do online Lipschitz, just the original definition. But you're right, there is a small, these are small technical details, but yeah, I prefer the online Lipschitz definition, but this one is slightly easier to work with. So we'll stick with that. Cool, thanks for the question. So yeah, so n competitive in general and log n for randomized, and we saw that those two results are the best you can hope for. Another theorem that I'm not going to prove because we're going to do more general things is that on uniform space for k-server, okay, so you remember k-server is this problem where instead of maintaining just one point, one state, you're maintaining k-states. Okay, and each time there is a request, one of them has to satisfy the request. So basically the question becomes, instead of choosing one point among maybe n, you choose one point among k. Okay, so it's a different type of complexity. And for k-server, you can also define the marking algorithm for the uniform space. The analysis is slightly more complicated, but what you will get is k competitive indeterministic and log k for randomized. O of log k. Okay, so independent in particular of the size of the metric space. Only k matters.
Could you repeat again the definition of k-server?
Yes. So now instead of maintaining a single state, you're maintaining k states, k distinct states. Each time, the request, the set, are singletons. You just get one element. You have to satisfy this element. But instead of having to, if you had to move the k points, this would be trivial. There is no problem. But the key trick is that the only thing that I ask you to do is that one of the k states satisfies the request.
And do I start with k already?
Yeah, you start with k already. So just to get some idea of what's going on, imagine that I have a line, right? And I have a server sitting here, a server sitting there. And maybe I get this request here. I mean, right here. Okay? So then the natural thing to do is to move that server. Okay, so now the new situation becomes I have one server here and one server there. And now maybe I get a request here. Okay, so now maybe I move again this server. And if I keep going like this, you see a greedy strategy, it will keep moving. But the best in hindsight would have to be to realize this and move that server over here and just have the two sit there and never move. This is very similar to the example that I gave you this morning with a 3-point, metric space for sets. Okay, good. And also one, so this again we won't prove, but I'm telling you. And another theorem that we saw this morning was that classically Steiner, the Steiner point is, let's say, O of D, O of square root D, let's say, Lipschitz. Right, this was in the classical sense, and we didn't say anything yet about the convex case for online Lipschitz. Yes?
Excuse me. In the first theorem, you're talking about the previous result, about the marking algorithm?
Yes.
But in that case, beta could be 0?
Yes.
Okay, so
Yeah.
strictly
Yeah. But if beta is 0, then you cannot take the minimum of a row 0. If beta is 0, then you have to take the maximum of a row 0. You have to take the worst starting point. So it's kind of, small differences, but in the big picture, in the philosophy of those results, it doesn't matter. But in the details, it does matter a little bit. Yeah. Okay, so this is what we have proven partially so far, and this is basically where easy things stop. So as soon as you move beyond those uniform spaces or classical Lipschitz for convex, any question is hard, or so it seems. So the field is now, I'm going to tell you a couple of conjectures which are exactly generalization of this. So in those cases to arbitrary metric spaces, and in this case to just online. And these have been opened for 30 years, and they are still open, and we don't know how to solve them. So yeah, it's a good opportunity. So the main conjectures, and I'm going to tell you a little bit about the history of the field. So the main conjectures are like this. Let's give them name. Theorem 1, 2, 3. So conjecture 1. Theorem 1 is true for any metric space, for any finite metric space. Okay, and by that I mean not that the marking algorithm is good, but that on any metric space you can get an order n competitive algorithm deterministically and an order log n competitive algorithm randomized. Conjecture 2. So this conjecture goes back to, I'm going to start putting names, to Borodin, Lignal, and Sachs in 92. So this is a journal version. These conjectures are actually from the end of the 80s. Second conjecture is that theorem 2 is true for any metric space. And here I don't really need to specify finite because, again, n doesn't appear. Okay, so again, and by this I mean I'm being a bit, I'm not being super careful. Actually, the conjecture is really this, that it's exactly k competitive and O of log k for randomized. And this is, so the first paper introducing the k-server problem was Manasseh, McGeoch, and I believe, let me make sure that I get this right, yeah, and Slater in 90s.
Excuse me.
Yes, please.
In the proof of theorem though, 2,
Yeah,
you use like something like the same marking algorithm?
yeah, yeah. The same marking algorithm is just the analysis. The analysis of k competitive is very easy, the same. The analysis of O of log k is slightly more tricky. It's this would be a slightly difficult exercise. It's, once you set up everything, it's just a couple of lines. But as I will explain now, these algorithms, these marking algorithms are like combinatorial type algorithms. And this is basically all we know about combinatorial algorithm. Then we will need more continuous technique to solve the general questions. So that's why I don't want to talk too much about this. Okay, so that's conjecture 2. And conjecture 3 Theorem 3 is true for online Lipschitz. Okay, so again, theorem 3 was just about classically, so in terms of classical Lipschitz nets, the Steiner point is square root d Lipschitz, and the conjecture is that there exists a selector which is square root d Lipschitz, but online Lipschitz. Okay, and we are far from the answer to each one of those. Yeah?
In that theorem, we were talking about the convex.
Yes, classically is O of square root d Lipschitz for the convex case. Thank you. Yeah. Okay, so, and this conjecture goes back to Friedman and Lineal in 92. And the situation was pretty dire for some of those problems until recently. So for instance, for conjecture 3, it was not even known if there exists an online Lipschitz algorithm, with any Lipschitz constant, say in dimension 3, in R3. So this paper, this first paper did it in R2, and in R3 it was open for 30 years. So now we know this. So this is some recent work. So here I'm going to try to put some of the state of the art. And then after I give you the state of the art, I tell you a little bit about the history. So the theorem, this is due to myself, Yin-Tat Lee, Yuan-Ji Lee, and Mark Selke. So we worked on this summer and many years before. Is that there exists 2 to the O of D online Lipschitz selector for the convex case, for convex. Okay, and again, I'm not going to explain what this algorithm is. It's not that complicated, but it's exponential in the dimension. So a great opportunity is whether you can get any polynomial. And of course, the final question of whether you can get square root d, that seems really hard. Even d would be really fantastic. Okay. By the way, the lower bound is very easy to prove. Okay, it's very easy to prove that you cannot do better than square root d. For conjecture 2, same thing. The situation was also pretty dire in the sense that it wasn't even like, as I will explain very soon, in terms of algorithms that only depends on k, that do not make appear the metric space, the state of the art was a beautiful paper of Papadimitriou and Koutsoupias in 95, where they proved that you can be 2k competitive. And this was the best we could do. So exponential gap between the upper and lower bound. And another paper that was a breakthrough at the beginning of the 2010s was that you can be polylog in k and n. Okay, so polylog in k and n is not necessarily better than k. If n is very, very large, it's not necessarily better. But now we know that you can be polylog k. So this is a combination of 2 works. One of them that I will tell you about, and the other one that I won't. So the 2 papers are, so it's myself, James Lee, Yin-Tat Lee, Michael Cohen. Sorry, Michael comes here. Michael Cohen and Alexander Madry in 17. And together with a paper by James Lee from 2018, we now know that you can be log to the 6k, log to the 6 of k competitive for k server. Okay, so this is the state of the art. Our paper, our joint paper, is easy-ish. So hopefully I should be able to explain everything. James' solo paper is difficult. It's really difficult. And this is the best we know right now on this problem. It would be very nice to have a slightly simpler viewpoint that gives you polylog k. We do not know that. And log k seems totally inaccessible right now. So the only one that was in good shape was conjecture 1. So now the state of the art is again basically the same team. So myself, James Lee, Yintat Lee, and Michael Cohen. And I keep putting Michael after, it's not fair. So Michael. So there we can get log squared n. So only a log n away. But this log n away is very fundamental. I won't have time really to talk about it in this course, but mostly instead of talking about general metric spaces, we're going to talk about tree metrics. So I will explain what is a tree metric. That will be probably tomorrow. But on tree metrics, we are able to get actually log n. Okay? And in fact, for K-server, on tree metrics, we are able to get log squared K. So very close to the conjecture. And then it is known from very general theorems that you can approximate an arbitrary metric space by a tree metric up to a log n distortion. Okay, so this extra log n comes from this distortion of approximating any metric space by a tree metric. And it's very fundamental because, as you will see, basically the techniques that we're going to develop are to use mirror descent or gradient descent on an arbitrary metric space. And then what we have to find is a notion of entropy that respects the metric information. And we found a formulation of entropy on a tree metric, which works perfectly. And the question is there such a notion for general metric spaces? And we do not know that answer to this question, and that seems to me very fundamental. Okay, so maybe a bit more about history. Is there any question on the conjectures and the current state of the art? Yeah?
So there is the best case for each conjecture?
Yeah, this is the state of the art. Any improvement on this would be very, very interesting. Yeah?
Conjecture 3 is only about deterministic selectors?
Very good. Excellent. So it turns out that for the convex case, you do not win anything by randomization. Here is the reason. If you have a randomized strategy, the support is contained in this convex set. So you can just average, you can output the mean of your distribution. That will also be in the convex set. And distances are only shrinking. So if you had to move this cloud of points to that cloud of points, the movement is bigger than if you just had to move the mean to the mean. So in fact, randomization doesn't help for the convex case. And it's why also things are of a slightly different flavor for the convex case compared to the other ones. Yeah. Yes? For what? Say again, sorry. Yeah. Yes. So you can assume that everything is from a shortest path on the graph. Yeah. It doesn't. You don't really lose generality by assuming that. Yeah. Yeah. So maybe just a few more words about history, just quickly, just to give you pointers of the most important results. And I'm not saying anything about lower bounds. Lower bounds are also very interesting, but we're very close to, I think, optimal lower bounds. Okay, so there are still little gaps, and the series that has been developed for lower bounds are really beautiful. It's called the metric Ramsey series. So Ramsey series is about finding structure in any in any possible configuration. There is always that structure or that structure. So metric Ramsey is about, given a metric space, what kind of sub-metric space exists in it. So you can, metric Ramsey is that basically there always exists, say, a large tree in your metric, things like that. And then once you have exhibited such a large tree, then you can do the lower bound on the large tree. Okay, so I won't say more than that. Really, lots of beautiful papers from the 90s and early 2000s. So just super briefly, so the story starts, in the 1960s. So that's when people started, that's, let's say, the birth of competitive analysis. So it wasn't phrased as competitive analysis, but there were papers on bin packing and things like that, which were competitive analysis flavor. Then really the field took off in the 80s, and there is a very famous and important paper by Slater and Tarjan from 85, which is doing K-server on uniform metric. Okay. Then there is a paper by Manas et al. Which introduces it on general spaces. And from the 80s to the 90s, this is like the reign of combinatorial methods. Okay, combinatorial methods. And in particular, if there are experts or if some people want to read about it, there is this work function algorithm which is very combinatorial in nature. So people have studied that, and the crowning achievement of this is Koutsoupias and Papadimitriou. From 95, which is a 2k minus 1 competitive deterministic. Okay, and this is this work function algorithm. It was really a breakthrough at the time. I mean, before that, things were exponential in K. Good. Then, in the early 2000s, for the finite case, there was a log squared n times log n. And this is Fiat and Mendel. 2003. So note in particular that this paper is only a log n improvement. Okay? To me, the improvement is not really about the bound, it's more about the technique. So here this was a combinatorial flavor algorithm that they had. Very, very clever, but tricky analysis. What I will show you is much simpler. Okay. And then after that, the continuous method started to appear. So in the end of the 2000s, early 2010s, there was what's called the primal dual schemas. And here the important paper is by Nikhil Bansal, Niv Burbinder, and Sefi Naor. This is from 2012. And what they got, it's pretty interesting. The uniform space, from now on, I will want you to think of the uniform space as just a star like this. Okay, so this is the uniform space. So all of those edges, they have unit lengths, let's say, and these are the location. Okay, and when you want to move from here to here, you have to pay this distance plus that distance. So say if the edge lengths are 1/2, then moving from a point to another one is already distance 1. And what those guys did was just log k for a weighted star. Okay, so these are just stars where there are weights on the edges. W1, W2, etc. up to Wn. But for such very simple metrics, we don't know a combinatorial algorithm. We don't know a simple algorithm. For that matter, for K-server on this, we don't really know a polynomial time algorithm. Polynomial in the sense that depends polynomially, say, on K and N. We don't know that. Okay, but this type of continuous space methods was able to give you log K for a weighted star. And then what I'm going to tell you about now, so now, is mirror descent. Okay, and mirror descent is going to give you, so we're going to see log squared K for a tree metric, which is just the metric, the shortest path distance on a generalization of this. This you can think of it as a tree of depth 1, but we're going to look at arbitrary depth trees, and we're going to get log squared K, and we're going to get also log N for the other formulation of the problem for a kind of special tree metric. I will explain. And here it's true also. It's also for a special kind of tree metric. And for instance, this conjecture, just to clarify, they are open on the one of the simplest metrics that you can think of, which is a line. Okay? And just to clarify also about applications of this, K-server on a line, it's a very, very real problem. I mean, you can imagine that you have a hard drive. Your hard drive is a line like this, and you have K heads, that can write. And say I want to access this information right here. Which head do I move? Okay, that's K-server on a line. That's just, it's real, it's true. I don't want to talk too much about applications because I think the math is really beautiful and there are many things to explain, but there are many, many applications. Same thing, in fact, for the convex case. Being competitive for convex functions, I will explain in a minute that you can do it with convex functions. There are many applications in resource management. You can look up, for instance, in Caltech. There is a group by Adam Weirman working on applications of this. Okay, so that's all I want to say on the history. Is there any question on this? History and conjectures and okay, and we are almost done with the introduction. The last section I want to tell you in the introduction is about cost functions. Okay, because the cost function actually will be very insightful. Okay, so 5 cost function version. So it's the same problem, but you replace a set by a cost Ct, which goes from x to r plus bar. And say Ct is in some set of cost functions. Okay, so now each day, instead of being presented with a set of feasible states, you're presented with a cost function on the state space. And the cost function is telling you how much you're going to pay if you stay in a certain state. So this is also called metrical task systems. Metrical task systems. And the name comes from the following interpretation, which I find reasonably insightful, which is that this cost function, you can think of it as a task. Okay, so you have your state space, you have an agent, you are an agent in the state space, and today there is a certain tasks that come. You have to complete this task. And the cost function is the completion time for this task in a given state. And once you see this task, you are currently sitting in a certain state, you can decide that to complete this task, it's better to first update your state, move to a new state, and complete the task over there. Okay, and you just want to trade off this movement of updating your state with completion time optimally. Of course, it's more general than what we had before, because a feasible set can just be viewed as a zero infinity cost function. Okay. But in fact, it's not more general. It's strictly the same, and that's why I started with sets, because these are actually exactly the same. So here is a theorem, and the proof is an exercise. Proof, it's the exercise for this hour. And let's say, there will be 2 statements. I'm only asking you to prove the first statement. If you can prove the second statement, great, but only the first one is expected, let's say. So here is the claim. So convex cost functions in RD can be reduced to convex sets in RD plus 1, RD plus 1, up to a loss of a factor 2 at most. So what do I mean exactly again? So we just said that, of course, trying to be competitive with respect to convex functions, it's a more general problem than being competitive with respect to convex sets. Okay, the function which is 0 on a convex set and infinity outside, that's a convex function. Okay, so it is more general. Now what I'm saying is that in fact the problem with convex functions in dimension d, you can solve it if you could solve the problem in dimension d+1 with convex sets. Okay, and you might lose a factor 2 in the competitive constant or in the online Lipschitz constant. That's what this theorem says. Okay, and it's not, you will see, it's fun to think about. Recently there was a paper that claimed that this is true if you have RD and RD. The proof turned out to be wrong, and we don't know whether it's true. Okay, so an open problem is whether it is actually true that you can reduce convex cost in RD to convex cost in convex function in RD to convex set in RD. I mean, eventually things are just true, that there is a competitive algorithm for both problems. So eventually it is true that you can reduce, but is there a direct proof? So we don't know that. And the second one is that arbitrary functions on x, where x is of size n, can be reduced to arbitrary sets on some x prime with the size of x prime which is at most twice. Okay, so you might just need to add a few states, but you can again reduce arbitrary functions to, in fact, arbitrary sets. And this reduction, let me just throw a technical term, which is HST, for hierarchically separated trees. So this is something that's going to be important. It's this special type of metric, of tree metric that I was talking about. This reduction, if you start with x being an HST, you end up with x prime being an HST. This is also important for the rest of the story. Okay, so this theorem shows to you that it was reasonable for me to start by only talking about selectors for sets. Okay, in fact, it also works for cost, and this is really the one which has more application, talking about cost functions.
Sorry, can you repeat the definition for cost? So
yeah.
Before you have the set, and you have to choose an element from the set, and you sum the distance at the end.
Yeah.
Here you don't have the distance. So
very good, very good, very good. So yeah, very good, very good. So let me introduce some terminology. In the cost version, there are now two types of cost. There is this, which is called the service cost, and there is the movement cost. So I'm going to call the service cost ST. Let's say S capital T is going to be the sum for t equals 0 to capital T of Ct of rho t. This is a service cost. And you also have the movement cost. The sum for t equals 0 to t minus 1 of the distance between rho t minus 1 and rho t. So now you have two types of cost. You have service cost and movement cost. And this will be very important.
Yeah, but now you don't have to satisfy the set. You have to just
now you don't have to satisfy. Yeah, you just have to.
Yeah.
And being competitive is with respect to the sum of both. Yeah. And now I'm going to introduce another terminology which is strongly competitive, and I'm going to explain what this means, and this will be insightful to derive algorithms and analysis. Okay, so just to clarify, yeah, the definition is that you are alpha competitive if the service cost plus your movement cost is comparable up to a constant beta to alpha times the best you could have done in hindsight. So let's call it ST star plus MT star. Okay, let's say this is the service cost plus movement cost of any algorithm, any type of movement. And now I'm going to say you're strongly alpha competitive if you have the following. Your service cost itself is just bounded by ST star plus MT star. So you are actually one competitive with respect to the service cost, and MT is bounded by beta plus alpha st star plus mt star. Okay, if you want, maybe let's say alpha minus 1. Okay, so you're strongly alpha competitive if your service cost is actually comparable to the best service cost plus movement cost. Let me just think if I want. Let me add a constant just in case. Okay. And we will derive algorithms that satisfy this. I will explain. Okay, so that's what we're going to do now. But let me draw your attention to the fact that, in fact, this inequality is very easy to satisfy. I have a cost function. I can just move to the minimum of the cost function. Every time step, I go to the minimum. This will certainly satisfy this. There is just no other algorithm which has a smaller service cost. So moving to the absolute minimum just satisfies this trivially. But maybe it induces a lot of movement. Okay? So this one is not hard to satisfy by itself. It's a combination of the two which is hard. And we'll see that this one is very naturally satisfied by gradient descent type algorithm. And then the question only becomes about the movement of those gradient descent algorithms. So that's what we're going to do now. Okay, so let's move to chapter 2, which is gradient descent approach. Okay, and we're going to start with a basic insight. And this is from online learning. Okay, so I'm not talking too much about online learning, but online learning is lurking behind on many of the things that we're talking about. For instance, it is in the online learning community that mirror descent was recognized as useful for sequential problem in the first place. I will explain mirror descent history. Okay, so let's focus on the convex case and let's lower the bar. Okay, so let us focus on the convex cost case and lower the bar. What do I mean? So I mean we only want to compete with a static opt. So a static opt is just someone, it goes somewhere and it never moves anymore. Okay? So what I mean by that is a minimum, say over y in Rd to the sum for t equals 0 to capital T of Ct of y. Okay, it just goes to the minimum of this sum of function. That's all this guy does, and we want to be competitive with this, with respect to this. And instead of asking for that the movement is also comparable to this, I'm only going to ask that you don't move too much. And I'm going to be flexible, you know. This is just, this section is not about deriving a formal result, it's just about giving intuition. So for movement, for algs movement, we only ask it to be small.
So, Sebastian, sorry, yes.
Yeah. Yeah, yeah.
So in the theorem, you say that you can reduce these to convex sets.
Yes.
But now you want to show this result now also for service costs.
Yeah. So very good, very good. So let me explain the philosophy a little bit. So the most elementary problem is the one with sets. That's the most elementary one. Turns out this one we do not understand it in some sense. What we will understand better is once we have a cost, because once you have a cost function, you get some intuition of where to go. You will get some gradients, you will get some local information. So in fact, the cost version is going to be easier to derive algorithm. At least in our current, okay, here is my point, is that with our current knowledge, it's easier to derive algorithm with cost, when there are costs. But I can see ultimately algorithms being designed for the set case as kind of the most canonical case. So that's why I wanted to start with this. And what I'm saying here is that we, you do not lose generality if you were just focusing on sets. Turns out that we don't know how to focus just on sets. So yeah, so this is the philosophy of what I'm doing.
But you mean when you assume that the functions have some are represented of some form, no?
So
It
you
give you more information.
no. So there are two theorems. One of them is if you have convex functions, then you reduce it to convex sets. And the other one is if you have arbitrary functions, you reduce it to arbitrary sets just by expanding a little bit the size of the state space. So even, this one is also telling you something, this second bullet point. This one doesn't assume any structure. Yeah. Notice that I didn't talk about K-server with cost. It's because we don't know how to do that, and maybe it's not doable. So, yeah. Okay, so now indeed, now we're talking about, now from now on, except when I talk, even in K-server, we're going to introduce an artificial cost because we don't understand how to work without cost. We need a cost to guide us. So from now on, there will be costs all the time. Costs are going to be what guides us. Costs are going to be on what we do gradient descent. This is what's going to happen. Yeah?
I don't get clear if you can make this reduction in both sides. I mean, you can solve the cost function with the sets and
Yes.
the other side.
So cost functions are strictly more, are more general than sets because you can always, this set, you can represent it as a cost function that is infinity outside and 0 on the sets. Yeah. Okay, so now we focus on we have a convex cost, okay? You get a convex function. You're sitting somewhere, where do you go? That's the question we want to ask. And what we're going to say is, again, to simplify, because we're not going to solve the general convex case right now in 20 minutes. So I'm going to lower the bar by saying we only want to compete with a static optimum. And I don't want really the movement. I don't want you to think too much about it. I just want it to be small for the moment. And small, you see it when, you know it when you see it, that it's small. Okay, this kind of small. And also is if, as we go in the discussion, we need to add assumptions about the convex functions, we just add them. Okay, it's just about intuition. Okay, so the strategy that we're going to look at is maybe the first one you would think of if you have some training in convex optimization, which is gradient descent. Okay, so right now you're sitting here at xt minus 1. Okay, so I'm also changing a little bit the notation. When I have a continuous variable, I'm going to use x to denote the variable. Instead, rho is for a discrete variable. So x is my continuous variable. And I get some gradients. Okay, so this is the gradient, the negative gradient of ct at xt minus 1. So because it's a convex function, I know that if I move in this direction, I will find points of a smaller value than xt minus 1. Okay, I know over here, I am locally decreasing, okay, if I go in this direction. So what I want to do, I'm currently sitting here, and I want to get to a point which has smaller function value, okay, where ct is smaller. And I don't want to move too much. So I'm just going to do a small step of gradient descent. Yes?
When you receive the function, what do you know about it?
I know the entire function. So, yeah, you could do better than gradient descent, if that's what you're thinking. That is true. But just as a first step, let's see what happens with gradient descent. But yes, you're right, you know the entire function. So you could say, let's try to minimize it in a small radius or something like that, in a small ball around me. Yeah, you could think of something like that. So the proposal is to do the following, is to set xt to be xt minus 1 minus eta grad ct at xt minus 1. Okay, you just do a small step in the negative gradient direction. Eta is a small step size. So if the gradient is controlled, is bounded, then this is small if eta is small. And the fact that the gradient is bounded just means that the functions are Lipschitz. So let me add this as an assumption. Also, CTs are Lipschitz. One Lipschitz. And by this, I just mean the gradient is bounded. Okay, so the movement of this, movement per step is smaller than eta. Okay, so we make a small step, a small movement per step. So now the question is, what can I say about the sum for t equals, say, 0 to capital T of ct of xt? Okay, does this compare to the best you could have done in hindsight? It's not obvious. But here is the key point. It's not obvious in particular because those functions are arbitrary. So maybe, those cost functions, they send us in a certain direction and they move us back somewhere else. They can make us do crazy things. It's not like there is a fixed function where I'm doing gradient descent. I might be moving all over the place. But here is the key insight. The key insight is the following. So notice that this is basically, this is, let's say, upper bounded by ct at xt minus 1 plus the movement, the norm of xt minus 1. This is just by the Lipschitz guarantee. So this is smaller than ct of xt minus 1 plus eta. Okay, so up to a term eta t, which we are not going to worry about for the moment, I just need to understand what is this ct of xt minus 1. So now, and again, this is the whole point of online algorithm, I need to talk about opt. What is opt? So opt is sitting somewhere. Opt is here, maybe. This is y. This is opt that we want to compare to. Now, here is the point. If ct of xt minus 1 is greater than ct of y, so if currently, locally in time, I am paying more than opt. Okay, so the inequality is not that, if ct of xt minus 1 is smaller than ct of y, good. I'm just paying less than opt. But what happens if I'm paying more? Well, the point is that by convexity, if I'm paying more, this negative gradient is pointing in the direction of y. There is a positive correlation between this line and that line. Okay, so then we move towards y. And to put it differently, we learn something about y. So this is the key point of online learning, online algorithms, all of those online problems where you have uncertainty, is that you want to say that when you make a mistake, and you will make mistakes, there is just no other way because you don't know the future. But when you make mistake, you want to say that you learn something. Okay, so your mistake, you should learn from them. I mean, this is just, in life in general, it's a pretty good advice. And for algorithms design also. Okay, so if you pay more, then you move towards y. And the way we're going to formalize this mathematically is through a potential-based analysis. So mathematically, we're going to use a potential, which I will denote psi t, which is the following. It's just the distance to opt. So it's 1/2, let's say, of xt minus y, the distance, Euclidean distance squared. And we'll see why it's a distance squared, and all of those things matter. So our potential is just going to be the distance to opt. And what we're going to say is, again, if we pay more than opt locally in time, then in fact we get closer to it. So our distance our potential shrinks. So let's see how this goes. Yeah. So again, picture xt minus 1, y is here. We move like that to xt. And what is this potential? This potential is the distance squared. Okay, so if you want the distance squared, you can think of it, it has something to do with the radius of the ball. Okay, so if you want, there is y and xt minus 1, and you have this ball here. Okay, so this ball, kind of the curvature of this ball is your current potential. And now you move to xt, you get a new ball, like this. And the question is, how does the radius square of that ball decrease compared to the radius square of that one? Okay, so let me make this a bit more precise. So let's just give names to those vectors, a and b. Okay, so the question is, my potential before was the norm of a squared. Right? This was the norm of a squared. Let's say this is 0. You know, this is 0, and this is a, and this is b. So a squared was my previous potential. And now my new potential is the point a minus b. Okay, b is the new center. So what is this quantity? Minus a minus b squared. Okay, this is what I'm looking at. A squared was my previous potential. This is my new potential. I can just expand the square. You see the norm of a squared is going to disappear, and what I get is 2 inner product of ab minus the norm of b squared. Yeah, please.
Why minimizes the cost at stage t?
Say again?
Why minimizes the cost at stage t?
No. So the question is whether y minimizes the cost at stage t, and no, that's not what y is doing. Y is some unknown point somewhere in space that is minimizing the sum of the cost functions. So this picture is only in this case if you are paying more than opt. This is not the picture always. Sometimes, you know, we will move away from the optimum, but then this is because the optimum is paying more than us. So we will do this balance in a minute. So this picture is only when y is paying much less than us, or less than us, then we want to say we get closer to it. Okay? And you see, the key point here that I want to make is that the correlation between those directions is exactly what controls the potential drop. Up to this term, which is like small, because we assume that we're making small movement. All of this, I want to clarify. We're in the intuition section. Okay, so everything I say is to give you intuition. We're going to derive formal calculations, but eventually there is going to be a lemma, a proof, and you know. So if you're a little bit lost, it's fine, but hopefully you're not. Okay, good. So let's see how to use this. So what I care about is ct of xt minus 1 minus ct of y. Okay, so this is the gap. This is my regret. This is the gap between what I pay at time t, you know, again, up to this little difference of ct of xt or ct of xt minus 1, but it doesn't matter too much, compared to what opt is paying. Let me introduce the gradient. So this is smaller than the gradient of ct at xt minus 1, inner product with xt minus 1 minus y. This is just convexity. This is a definition of convexity. Just saying that, you know, the function is above its tangent. Okay, ct is above its tangent. But now, what is this? By definition, the gradient, it's this step. Okay, so this is equal to 1 over eta, because I do a step of size eta, and then I'm just going to change the sign. I get xt minus 1, inner product with y minus xt minus 1. Okay, so it's exactly this inner product that I was talking about in this little calculation. My regret is exactly bounded by the correlation between the direction I'm taking and the direction to the optimum. So the bigger my regret, the stronger the correlation. The more I regret, the more I learn. This is exactly what we want. Okay? And now the way to formalize this is through this potential analysis, and it's very easy because this inner product, we just said with this formula that it's the drop in potential up to this small term. Okay, so what is this equal to? This is equal to 1 over eta, and then we're going to have 3 terms. So what is A? A is just y minus xt minus 1 squared. Then what is A minus B? A minus B is just y minus xt minus y minus xt squared. And then we just have this term plus b squared, and b squared is just this distance, plus the norm of xt minus xt minus 1 squared. Okay, so you get your regret is bounded by exactly the potential drop, plus a little term which we're not going to worry too much about, and I will explain a little bit more why we don't worry too much about it. Okay, so let me just finish. So this means ct of xt minus 1 minus ct of y. This is upper bounded by 1 over 2 eta, and then I get psi t minus 1 minus psi t. And again, what is this term? This distance is at most eta. That's the calculation we did. So this is at most eta squared. So we get plus eta over 2. There was 1 over 2 missing here. Okay, so when I sum, I get that the sum of the ct xt minus 1 is smaller than the sum of cty plus psi 0 minus psi t over 2 eta plus eta t over 2. So I get that my algorithm indeed has a service cost comparable to the service cost of the optimum up to this, which is just an additive constant, right? I mean, psi t, note that this is smaller than, this is just smaller than x0 minus y squared over 2 eta. And there was no 2 here, there's no 2. Okay, so this is just some constant that depends on eta. So when eta gets smaller, this constant gets worse. And this is, hopefully, if eta is small, this is something small. Okay, so we achieved our goal of having a good service cost and hopefully a not too big movement. Yes? What? Yeah, we did. Because when I say that this distance is small, this is really the norm of the gradient. So I am using it. Okay, so this approach does not solve online Lipschitz for convex functions. By the way, online Lipschitz for convex function, it has a very beautiful name, which is convex body chasing. Okay, so this is the name of the problem, and I will from now on refer to it as convex body chasing because that's what everybody uses. So this approach does not solve convex body chasing. Okay, and the reason is because you cannot really, gradient descent is moving too much. So you need something else that moves less, and the right thing to do is to do something like cutting planes. So cutting planes, they make less movement, but they make bigger steps. And this is the appropriate thing to do in this case. But this was just to give you the insight that gradient descent has this very nice property that when it's paying, it's learning. Okay, it's getting to a better point. So now so this was a proof in discrete time, and everything we have talked about so far was in discrete time. I'm now, for the rest of the class, gonna move to continuous time. And I wanted to do it in discrete time so that you can appreciate how easy it is to do it in continuous time. So I'm going to reduce this proof in continuous time, And you will see it's just trivial, and that will be very useful when we move to mirror descent. So 2. Yes?
How do you implement the algorithm if you don't know why?
Good. So in the present case, the algorithm was, I erased it, but you're sitting at xt minus 1, you compute the gradient, and then you do a small step in the gradient direction. So you don't need to know why. But this type of question is going to come up when now I'm going to start to talk about continuous time, and instead of gradient descent, I'm going to talk about gradient flow, which is just a continuous time gradient descent. Whether this is an algorithm or not, I leave it up to you guys, but it's a method, it's a technique, it's a selector, certainly. So, okay, so simpler analysis in continuous time. So we have a lot of work to do, right? I mean, right now I'm comparing to a stupid fixed static opt. So I need to talk about what happens when opt is also moving. We have a lot of things to do. What about the movement? Okay, so but all of those things are going to come together naturally. So what I'm going to do in 2 is, for instance, show you that in continuous time it's very easy to see what happens when opt is also moving. So let's do it. So now Ct. T is now a continuous time parameter from x to r plus bar. T is now in r plus, is a continuous time cost path. And we respond to it with a continuous time algorithm, xt. Okay, maybe let me do it like this right now. Let's say we're still in RD. Okay, so we have this continuous time path, and xt is a continuous time answer. So now the service cost is an integral. It's the integral from time 0 to time capital T of the continuous time cost applied to the continuous time answer integrated with respect to time. And the movement is the integral of the norm of the derivative. Okay, instantaneously, how do I move? It's the derivative that tells me how I move. And the norm of the derivative is the instantaneous movement cost. So this is the norm of the derivative with respect to time of x of t, the norm dt. Okay, it seems, why are you doing this to us? We were so nice in discrete time, and then we moved to continuous time. But you will see. It's worth it. So let's rewrite our potential, right? So our potential was psi of t, which is 1/2 of the norm of x of t minus y L2 norm squared. And what is our algorithm? Our algorithm is a time derivative of x of t. It's just minus the gradient of ct at this current point. Okay, there is no t minus 1. Okay, so this is the dynamics. So from now on, we're going to talk about the dynamics of algorithms. So this is the dynamics. The way you evolve is you see continuously a convex function which is changing, and as you're moving, the gradient is changing, and you're just following the gradient. Okay, so this is the appropriate continuous time dynamics. And again, we're very soon not going to talk about convex cost. We're going to talk about linear functions, and it will be even simpler to think about it, so really don't worry about it. We're still in the intuition land, okay? Soon we're going to move to the formal land. But let's see what happens now when you differentiate psi of t. Okay, and the key point is that the derivative of x squared is x. Okay, that's all that matters. And that's why you put a square on this norm. Okay, so the derivative, and yeah, okay. That's all I'm going to say. So the derivative of psi of t It's just, view this as it's the inner product of this against itself. So when I differentiate, I get twice, this against its derivative. And the derivative of this is just the derivative of xt. So I get d over dt of x of t. And this inner product with x of t minus y. Which is by definition this gradient. Okay, this is by definition equal to minus the gradient. So let's say gradient of ct of x of t inner product with y minus x of t. And this is bigger by convexity than ct of y minus ct of x of t. This is just convexity. Okay, in the future, when we will have linear functions, we will not even need this inequality. But you see now all of those lines and this picture, it's just all summarized by this derivative calculations. You see that your regret is exactly bounded by the time derivative of the potential. That's it. That's it. So if you're paying much more than the optimum, then this is, and probably I took it wrong. This was the other way around. Sorry about that. So if you're paying much more than opt, then this is very negative, and the potential is dropping. The time derivative is negative. Okay. And if opt is paying much more than nu, then yes, this can go up, as we will see. But that's how the potential is moving. As opt is sitting somewhere and it's paying much more than nu, then the potential goes up, and then you get closer, the potential goes down. So this is how things work. So you see, it's very, very nice. And now, I want to bring your attention to the fact that now we want to talk about a y that is moving also. So what about dynamic y? Okay, so now I'm just going to say psi of t is just 1/2 the norm of x of t minus y of t squared. But again, when I take the derivative of psi of t, I will just get two terms. I will get one term which corresponds to the derivative with respect to x, and one term which corresponds to the derivative with respect to y. So I will get, this term, ct of y minus ct of xt, plus another term which comes from the derivative of y, which is d over dt of y of t, inner product with y of t minus x of t. And let me assume for now, for simplification, that this term, assume this is bounded. So you never go too far from the optimum. Again, this is just for intuition, we will formalize it. But assume this is bounded by d in norm. Then I can just apply Cauchy-Schwarz, right? So the inner product is bounded by the product of the norm. So this is going to be bounded by two terms. I get ct of y minus ct of xt. So this is my regret. Plus d times the norm of the derivative of y of t. But what is this? This is exactly the movement cost of opt. This is the movement cost. Move of opt. Okay, so you exactly get that you're going to be able to compare to, sorry, and this is a y of t. So you exactly get that your service cost is going to be comparable to the service cost of any dynamic path. But you need to also take into account the movement of this. Okay, so we didn't work much more, but you got this very nice result that now, in fact, it works for any dynamic opt. Opt can move as long as you also take into account the movement of opt. Okay, is there a question on this? Yes. I will finish in 5 minutes.
I mean, why in this continuous case you want a dynamic y and not the static optimums as the before?
Okay, so the question is why in this continuous case do you want a dynamic y? So it's not really that in this continuous case I want a dynamic y. I want a dynamic y for the discrete problem. It's just it was going to be a bit annoying. I would have had again to do some pictures, etc. All I'm showing to you here is that when you move to continuous time, it's very, very simple to see what happens when y is also moving. It's just, you know, by the chain rule, it's just another line. You just add the derivative with respect to when y is moving. You can think first x moves and then y moves. And you see what happens to the derivative of the potential. Okay, so what comes next? So this was just for the intuition. So what we're going to do tomorrow, in fact, now I realize that I should revise a little bit what I was planning. So we'll probably do one lecture on K-server. And tomorrow what we're going to do, so tomorrow, so right now we don't have anything, right? We don't have real results. I mean, we're falling short on every count. Like the movement is just small, but it's not comparable to opt. This is about you know, moving in RD, but eventually we want this discrete space. So what we're going to talk about is mirror descent, where what it means is just that gradient descent is very Euclidean. And what do I mean by that? I just mean that xt minus 1 minus eta, you know, let's say gt minus eta gt. This is the same thing as, so say xt is this. It's the same thing as saying that xt is the argmin, is the minimizer of the linear function eta gt plus a penalty for moving away from xt minus 1 plus 1/2 the norm of x minus xt minus 1 L2 norm squared. Okay, so these two things are the same thing, okay? Doing a small step of gradient descent or minimizing the linear function plus a penalty for moving away from the previous point. It's very easy. You just look at the first order optimality conditions. And here you see the Euclidean norm. Here maybe you didn't see the Euclidean norm, but here you see the Euclidean norm. Okay? And the Euclidean norm is not going to be adapted for what we want to do because tomorrow, so we want to do randomized algorithm on a finite metric space. So what it means is that we're moving a probability distribution. So xt, instead of being in all of RD, is going to be in the simplex. And if you're just moving in the simplex, there is no reason to look at the Euclidean distance. So what we'll do is we will replace the Euclidean distance by the most canonical distance on the simplex, which is the Riemannian distance induced by the entropy. Okay, and this sentence makes perfect sense, and I will explain that tomorrow. And once you do that, so mirror descent with entropy, what's going to happen is this will correspond to what's called multiplicative weights, which you have heard maybe in other places. It's a very famous and popular algorithm in many places. So multiplicative weights is nothing but mirror descent with the entropy on the simplex. And what the dynamics will look like is that it will be of the form x prime is like the cost at x. Something like that, okay? I'm being very, very imprecise. But the time derivative is going to be proportional to your current cost at this point. And this means that the movement is going to be related to your service cost. But the service cost, just by the analysis of gradient descent, so this is going to be by gradient descent type analysis, which is just, we will just have to generalize the analysis of gradient descent to mirror descent, but just this generalization is just calculation like this, nothing more fancy. This is going to be smaller than opt. So you will get your movement is comparable to the service cost, and the service cost is comparable to opt, and that's it. We will be done from there. Okay? Okay, so that's the plan for tomorrow. I will show to you mirror descent, why it gives you those dynamics, and then apply it to the weighted star. Okay, so the weighted star was W1 to Wn. I will show to you how you get an algorithm like this, and then I will do it for more general trees, and on Wednesday we will do K-server. Okay, that's it.